Welcome back to Numerical Analysis. It's Wednesday, April 15th, and today we're going to introduce the idea of higher order ordinary differential equations. But first, let me take a minute to apologize for the length of time it's been since I've been with you. Uh, Last Thursday and Friday, there was some personal business and departmental business that came up, and that took away some time. And anyway, you know how things happen. Uh, my other classes also, I've been working on those. And so, anyway, I'm doing the best I can, and I think almost everybody here is doing the best you can too. So I appreciate that. I'm going to have a little message for you probably tomorrow where I'll outline our end of the semester strategy and plans. The basic idea is that I'm going to make the final for the class optional. And so I'll lay out exactly what that means in the next video I post, which again should be able to get up by tomorrow. And so if you've done well, you know, on the homeworks up to now, and if you did well on test one, then you might consider not taking the final. But if you feel like you need to boost your grade, I do want to offer the opportunity to have a final exam so you can do that. So anyway, more details on that tomorrow. And also, let me say that I am way behind on grading homework, and I'm working on that, and I will get that done by this weekend. And so by the beginning of next week, which will be our last week of actual classes, I guess if you want to call it that, you should have a pretty good idea of where you stand in the class. Okay, so with that said, let's talk about the idea of higher order ordinary differential equations. And I thought we could start with just some examples. So I'm using z here to denote the function that satisfies the differential equation for reasons that will become clear in a minute. And so higher order equations basically involve higher order derivatives. So here I'm showing some second order equations. These will be equations that involve derivatives of order either 0, 1, or 2. So you see this first example, d squared z over dt squared plus z equals 0. The derivatives are of order 2 and of order 0 here. So it's called a second order equation because the highest derivative that's involved is order 2. The second example here is a little bit more involved. T squared times the second derivative of z with respect to t plus t times the first derivative plus t squared times the zeroth derivative is equal to 0. This is again a second order equation because now we have derivatives of order 2, 1, and 0 appearing. And then a third example, d squared z dt squared equals t times z, again is second order because the highest order is derivative is order 2. I should point out that these are all called linear equations, linear second order equations. And that's because the derivatives themselves of order either 2, 1, or 0 all appear only to the first power. To the first power. You don't have any, they're basically linear combinations of these derivatives where the coefficients of the linear combination can be functions of t, but you don't ever have something like the second derivative squared or the second derivative times the first derivative. Those would be nonlinear equations. So these are all second order linear differential equations. Actually, these are all pretty famous differential equations. The first one here, d squared z plus z equals 0, is actually an equation whose fundamental solutions involve the sine and the cosine function. You can verify easily that the general solution of this differential equation is z equals some constant times cosine of t plus another constant times sine of t. And so the second equation is actually a famous equation from mathematical physics called Bessel's equation. Bessel was a 19th century physicist, and he studied this in the context of physical problems. And the equation has turned out to be extremely useful in all sorts of branches of applied mathematics, including, mathematical physics, but also probability theory, signal processing, lots more. And so there's Bessel's equation. The third equation here is called Airy's equation. Airy was an English astronomer and physicist, and again, 19th century. And so shout out to the physicists here. They gave us some enduring examples of second order equations that continue to be important today in applications. You might be wondering about the solutions of these two equations. Well, like we saw with first order ordinary differential equations, generally these things don't have elementary solutions, and that's true of both Bessel's equation and Airy's equation. They do have solutions, but the solutions can't be written down as finite combinations of basic functions from calculus. And so the importance of accurate numerical methods is highlighted by these kinds of examples again. So what are we going to do with these then? Well, there's kind of a standard technique that is used not only for second order equations but for higher order equations, and that is to reduce a second order, or generally a higher order equation, to a system of first order equations. So this is the process of reduction of order. And let's see how it would work with that very first example. This guy, the second derivative of z plus z itself adds up to 0. What we want to do is introduce two new variables. The first one I'm going to call x, and I'm just going to set it equal to the unknown function z itself. And then the second variable I'll introduce, I'll call it y, and I'm going to let it be the derivative of z. And then what we do is we work out the differential equations for x and y and keep them first order. So let's look at the first derivative of x here. dx dt would of course be equal to dz dt. But dz dt we already know is y. So that says that dx dt is equal to y. Okay, so let's look at y now. What about dy dt? Well, remember, y was dz dt, so the derivative of y will be the second derivative of z, and that's what I'm saying right here. Okay, what's the second derivative of z? Well, here, go back to the original equation and solve for that second derivative of z. The second derivative of z would just be negative z from that original equation. So that's where that comes from. But of course, z was equal to x, and so negative z is equal to negative x. So dy dt is equal to negative x. So if we put all this together, we get this first order system. dx dt equals y, and dy dt equals negative x. The idea here is that this is, first of all, both these equations are first order, so I don't have to deal with second derivatives. And secondly, I took care to write the derivatives of x and y in terms of both x and y themselves. I didn't want z to appear in my first order system. So this first order system is equivalent to that original second order ODE. And this is a process you can use on any higher order equation to reduce it to a system of first order equations. So let's take a look at one more example. Oh, and I just wanted to point out that before we went on to the next example, that this first order system here that's equivalent to our original second order equation has a general solution for both x and y, right? X, it turns out, is c0 cosine of t plus c1 sine of t. Remember, x was equal to z, so it's not surprising that the solution for x is the same as the solution for z that we saw back in the very first couple of slides. And then y it has this form here. So we do have a solution to the system, and the solution of the system means two functions, the solution for x and the solution for y. Okay, so let's look at how the reduction of order process works in Airy's equation. So Airy's equation, remember, d squared z dt squared is equal to t times z. So again, the idea to reduce this to a first order system is to let x be the original unknown function z and let y be the derivative of that unknown function. And then we want to write the derivatives of x and y in terms of x and y themselves. So dx dt would be dz dt, but we know dz dt is y from our original substitution. And dy dt would be what? Well, it'd be the second derivative of z, and then go back to the original equation. The second derivative of z is just t times z, but we know that z is equal to x, and so we get t times x. So dy dt is t times x. And so Airy's equation is equivalent to the first order system, dx dt equals y, and dy dt equals t times x. So again, we perform that reduction of order of a second order equation into a system of two first order equations. And on your next homework 24, I believe it is, I'll ask you to do the same kind of thing. So what do we do with this? Well, once we have a first order system here, we can apply Euler's method in pretty much the same way as before. We're going to use Taylor polynomials for the unknown functions x and y and go through that process of projecting the solution forward from current values. The key to that is finding the Taylor polynomials for the first order system you have. So let's see how that plays out with Airy's equation. Suppose that at time t equals some value t sub n, so n here just means the current step, n might be 5 if you're at the fifth step of the solution process. Suppose at time t equal t sub n, the currently computed solution values are x equal x sub n and y equals y sub n. So x sub n and y sub n would be known, numerical values that we have. The question we want to look at is, what is the first degree Taylor polynomial for the unknown solutions x and y centered at that time t sub n? So let's consider x first. Let's call the Taylor polynomial for x just p. So p1 to indicate we're talking about a first degree Taylor polynomial. And here I'm just writing the generic form of the first degree polynomial for a function x centered at time t equals t sub n. So it'd be x evaluated at time t sub n plus x prime evaluated at t sub n, and then times t minus t sub n. So this is just the general form of a first degree Taylor polynomial centered at t equal t sub n. So the process is to find out what these values are, x of t sub n and x prime of t sub n. But x of t sub n is just x sub n. That's because we're essentially assuming that at time t sub n we've computed what x is. It's x sub n. So x of t sub n would just be x sub n. And x prime of t sub n we can get from the ODE again. So this is similar to the process we've seen before. Remember, our ODE said that x prime is equal to y, right? I'm going back, in other words, to this. The derivative of x is equal to y. That's from our original system for Airy's equation. So x prime of t sub n would be the derivative of x evaluated at time t sub n, but from Airy's equation, we see that that's y evaluated at time t sub n, and so that's y sub n. So x prime of t sub n is y sub n. So the first degree Taylor polynomial for x would be x sub n plus y sub n times t minus t sub n. And again, I'm just using what I know about x prime of t sub n, namely that it's y sub n, and x of t sub n, and then plugging those into my generic form there. So there we have the first degree Taylor polynomial for x. What about y? We need to find its first degree Taylor polynomial too, because remember now we have a system. We need to find the Taylor polynomials for both x and y here. Well, I need to call the Taylor polynomial for y something different because I've already used p for the Taylor polynomial for x. So let me call it q1. Okay, so here's just the generic form of the first degree Taylor polynomial for y centered at Tn. And now let's use what we know. Y at time Tn is y sub n, and that's coming, remember, from our assumption that we've got a computed value at step n for y sub n. So y of t sub n is yn. And what about y prime at t sub n? Well, that comes from the system of equations again. So y prime at t sub n is dy dt evaluated at t equal t sub n. But dy dt is just t times x. So when I evaluated that when t is equal to tn, I get tn times x at time tn. But x at time tn is just xn, so I get tn times xn. So y prime at tn is tn times xn, and then I'm just going to plug that in right here on the next slide. So I do that, and I get this as my first order Taylor polynomial for y. Yn, that's y of t sub n, right, plus tn times x sub n. Remember, this is our y prime of t sub n, and then times t minus tn. So now with P1 and Q1 in hand, we can use Euler's method to compute an approximate solution in the same way as before. So let's consider our IVP. This is just the system for Airy's equation, and I put some initial conditions on it. My initial conditions I just decided to take at time t equal minus 3. We're saying when time is t equal minus 3, x is 1, and y is negative 1. So this is an initial value problem for a system of equations. You need to give initial values for both x and y. Let's use Euler's method with step size delta t equal 0.1 to compute an approximate solution. Okay, so the key thing here is to use those Taylor polynomials that we just computed to project the solution forward. And we'll do that in the same way as we have been. That is, the next time step is the current time step plus the step size, delta t. We're going to use 0.1 for that. Then the next solution value for x, we're going to plug that next time step, tn plus 1, into the polynomial for x, that's p. And the next time step for y, we're going to plug tn plus 1 into that next polynomial, into the Taylor polynomial for y, which is a q here. So that's how we'll project the solution forward. Let's get started. Step 0 is just to initialize the t, x, and y values. So t0 is negative 3, x0 is 1, and y0 is negative 1. And that's just coming from our initial value problem, right? The initial time is negative 3, the initial value of x is 1, and the initial value of y is minus 1. So that's where that's coming from. And then I'm going to go to the next step. So in step 1, we first compute our Taylor polynomials, p and q. So here's where I'm using these values I computed a few slides ago, p1 xn plus yn times t minus tn, and q1 yn plus tn xn times t minus tn. What I do here, though, is I use the most recently computed values for xn, yn, and tn in order to get those. So here, I'm plugging my x0, y0, and t0 values into that formula for P1 to get this. And so that's what you get. And I'm not going to, you could obviously simplify that, but let me not do that because we can just work with it as it is. I just kind of want to show how the pieces fit together here. Similarly for Q, I'm using my Taylor polynomial for Q with y0, t0, and x0 from the previous step, right? So that's what's happening here, and that's what I get. And again, that obviously simplifies. They'll simplify into linear equations in T, but let me just leave it that way so you can see where everything's coming from. Then once you've got those two guys computed, you project forward. So T1 is my T0 plus my delta T value, so that's -3 plus 0.01, that's -2.9. X1 is what I get when I plug T1 into P1. So I'm doing that right here. That turns out to be 0.9 once you crunch the numbers. And Y1, I'm plugging T1 into Q1. And so that's giving me the -1.3. All right, once I've got T1, X1, and Y1, I'm ready to go to the next step. So let's go to step 2. Again, we do the same sort of thing. We update our Taylor polynomials using the values from the previously computed solution. So now P1 is x1 plus y1 times t minus t1. Compare that to the previous step. We're just using the same thing, except we're just using the previously, our most recent solution values. And so that's what you get. Q1, you do the same thing, and that's what you get. Again, I'm not simplifying. Hopefully you can see where everything's coming from. And then you project forward. T2 is the T1 value plus the time step, which is 0.1. That gives us -2.8. X2 is what you get when you plug T2 into the Taylor polynomial for X, which is P1. So I'm doing that here. You just plug T2 into that, and you get 0.77. And Y2 is what you get when you plug T2 into Q1, and that turns out to be -1.561. And the process continues. So I'm just showing you here what you get when you carry this out a couple of more steps. You could actually use this if you want to. You might want to just go ahead and try this by hand yourself. Go to step 3 and step 4 and see if you can make sure you get the same values I got here. Of course, I went ahead and plugged this up and plugged this into MATLAB, and I'm plotting the solutions here. The red solution or approximate solution is X. The blue is Y. And so there you see I've carried the solutions forward from time t equal -3 to t equal +2. So you can see what the computed solutions look like there. I would point out that there's going to be error in those solutions because we're using Taylor polynomials, which are only approximate. And so the next step in this process would be to look at higher order Taylor polynomials to make Euler's method more accurate. And then the idea of controlling the error by keeping track of an estimated error at each step size and computing the step size to keep that error into control. Those are the same kind of things we did in our previous work with Euler's method for first order equations. And we'll look at how that process works for systems of equations in our next meeting. So similar kind of thing here. And I hope that made sense. If not, give me an email. I will be posting homework 24 pretty much concurrently with this video. And I'm going to make that due Friday night. So there is time to get in touch if you have questions. In the meantime, stay tuned, stay healthy, and I will be back in touch very soon. Y'all take care.